Today, the goal of this video is to show you the results of my bachelor thesis that I've been working on this summer semester 2024. The goal of the thesis was to develop a Micromouse hardware from scratch. So this is the hardware I ended up with. All of the different features are functional separately from each other, but I did not manage to do some maze solving in the scope of the project because there was just too much. The feature that I implemented on this mouse are the microcontroller, which is an ESP32S3. I have the 5 distance sensors on the front that are time of flight distance sensors, 2 small DC motors with magnetic encoders. The battery is a 2-cell LiPo battery. And on the other side of the robot, I have the dual motor driver, the buzzer, and an accelerometer. I also developed custom caster wheels that were small enough to be put on this robot. They are 3D printed and use ball bearings balls, and these I have on the front of the back these flexible 3D printed bumpers. So let's turn it on. Firstly, I'll just plug in the USB cable to the microcontroller. So now the robot is just connected to my computer. You have maybe heard the buzzer indicating that the robot is turned on. You can also see the small yellow LED that is blinking. This is the lowest level thread, so it indicates that the software is running properly. The red LED that is blinking indicates that the battery is empty. So now let's switch to the IDE. I am using Visual Studio Code with the Platform IO extension, which allows me to program pretty much any board. I will open the serial monitor of Platform IO, and this will allow us to communicate directly with the robot. You can still see the LED indicating that the battery is empty, and right here in the serial monitor we also get a warning with the battery voltage. It's 0 volts, obviously, since I did not connect the battery. So let's do that so it stops blinking. I just plug in the XT60 connector, and you see 2 LEDs lighting up indicating that the battery is also connected. And the warning messages stopped appearing. So now we have this serial interface which is opened. What can we do now? The first and most useful command would be using H for help. It shows you all of the different menus that are accessible. One thing I would like to show you would be firstly the debug. So now our robot is connected, it's powered through the battery, so we can try to see if all of the different sensors work. By typing D, I can see all of the debug modes, and for example, we could go and check what the values of the distance sensors are. To access this, I have to use the command A, and I could type A1 for the distance sensors, enter, and now I can see all of the distances of the 5 sensors. If I move my hand in front of the robot, I will see the values change. I type A0 to stop this debug. And as you could see in the debug, there are a bunch of different debug features that have been implemented, which are very practical to see, verify if all of the sensors are working properly, and so on. So the second thing I would like to show you would be the Wi-Fi utilities, because we need to configure the Wi-Fi in order for me to show you the remote debug interface. So let's check the Wi-Fi information. Right now you can see the password of the Wi-Fi, but the SSID is not configured, and so I have my small Wi-Fi router behind me, which is called Algernon, like the robot. So I will just configure it to connect on Algernon. And the Wi-Fi is not connected. Now it is. So this will be useful in a second. I will just show you one last feature, which is the, whoops, that was not the correct command I wanted help again. The print variables, so the P menu. If I type P, I can see all of the things I can show, and for instance I can show the state of the robot, which is the big object containing all of the robot's variables. So with PS I can see all of the data of the robot. I can see the odometry. I'm currently at 0 speed, 0 position basically, the distances, the IMU data, so the accelerations, the battery, and so on. So right over here I have a list of serial parameters, so they have all this uppercase letter, which is a code for each of the commands, and I have all of the variables that I can read and write in here. So for instance, I could try to make the buzzer do a sound. So with command D, I could type D2 for instance, activate mode 2, and make it make a sound. D3, D4, D5. I didn't define a mode, so nothing happens. We could also do the same with the LED. We could control it by hand, change the intensity, the color, and so on. And we can also control the motors through here. So let's do an example. Quick example. Right now we have the robot mode, which is the main parameter that says if the wheels are moving or not. I can check T enter, it's at 0, so that means that the robot is stopped. If I type T1, the wheels start turning. The speed of the wheels is also defined in one of these parameters. So typically it would be the linear speed or the motor's command over here. I've shown you the serial interface. It is practical to debug some of the things of the robot. However, in real life, I would not have this USB cable. I can't connect it because the robot would be moving on the table and I cannot keep a cable connected to it. So let's take this cable off. Now my robot is sort of autonomous, even though it is connected on the Wi-Fi. And what I want to show you is the debug interface I have programmed in order to visualize all of this data over Wi-Fi. By pasting the IP address of the robot in the browser, I can access the debug web page. So now I'm connected, and you can see directly that I get some real-time data of the robot. For example, the accelerometer's data is displayed, the linear accelerations, the angular accelerations, and you can see that along the Z dimension I approximately have -1 g, which makes sense. If I move the robot, I will modify these accelerations along the different axes. Again, if I move my hand in front of the sensors, you will see how the distances change. So now, for instance, I have my hand in front of the front sensors, and the front value is smaller than before. If I remove my hand, it will increase. Next, we can see the distance sensors values. I am displaying in this plot the 5 distances. The distances on the right side are displayed as negative, and the ones on the front and on the left side are as positive. So you can imagine being along the axis of the robot and having the right sensors negative, the left positive, which allows you to sort of visualize the distances instead of having them all positive. For the odometry, so the odometry is basically the measurement of the position and the orientation of the robot in the plane. To show you how this works, if I move one of the wheels by hand, you will see that the robot thinks that it's actually moving. It's moving on a circle because I'm moving only one of the wheels, so it's as if it was rotating around the other wheel. I want to show you how if I move the robot on my table, it will actually move in this plot. So I am moving the robot, and you can see that as I move it, the position and orientation of the robot are changed in the debug interface. After the odometry, I would like to show you the different control modes. They are 5 of them, but let's say only 4 because one of them is just being stopped, which is not the most outstanding. The second control type that I called same PWM is when I send the same command to the 2 wheels, which are independent. If I turn it on, you can see that the wheels start turning, but I can stop them very easily by touching the wheels. Again, if we go check the command, we have exactly the same command for the 2 wheels. It does not change if I touch the wheels. If I click on the wheel speed control mode, that one is basically I have a PID controller for each of my wheels independently, and it controls the speed in RPM. So I could turn it on and set it to, for instance, 300 RPMs, and the speed will be kept constant, relatively constant, even when I try to slow it down. If we go check the wheel speed, you can see here that it is relatively constant at the target speed of 300, and it varies a bit, but it's reasonable. The robot speed control is one of the most interesting ones, where I can control simultaneously the linear and angular speeds of the robot. So I can set this to 0.1 meters per second, 0 degrees per second, turn it on, and the wheels start spinning slowly and at the same rate. If I put the robot on the table, it will go forward very slowly. Alright. On the other hand, if I turn it to 0 and make it only rotate on the spot, it turns. The final feature that I implemented is to stop when an obstacle is detected. This is useful if I put it on the ground and don't want it to bump into everything it has on its path. Let's show it with 300. It's going to be more smooth. So I set it to 100, 300. I start it, and whenever I take my hand closer to the robot, the wheels stop. And you can also see that the LED on the microcontroller turns blue, which indicates that an obstacle is detected. Finally, if I press the button in the center, I also switch to this stop when obstacle mode. So I can also modify this mode using just the mouse without any interface, be it the Wi-Fi or the serial monitor. As I mentioned before, you can modify the parameters of the PID controllers through this interface. So you can directly see how the different values of the parameters impact on the controllers, which I personally find very interesting because it allows me to see how these different contributions act on the robot's behavior. I also allow you to independently turn on or off the angular and linear controllers. So let's just see quickly what happens if I do that. Let's set it to 0.1 meters per second and 0 degrees per second. So by default, they are both enabled. The linear and angular regulators are both enabled. And you see that, alright, both wheels turn approximately at the same speed and try to compensate if I touch the wheels. However, if I turn off the angular speed controller, suddenly, if I touch one of the wheels, the other one will just speed up to compensate for the first one having a 0 speed. And if you look at the plot, the linear speed is kept constant. It's just that the angular speed is not controlled anymore and will drop to 0 or just oscillate. But the linear speed is kept constant, which is the goal of this controller. And I find this effect really interesting. On the other hand, let's try the opposite. If I turn this one back on, I again have a control on the angular speed that tries to keep it 0. It's not very good right now, but tries to keep it 0. And if I turn the linear speed to 0 and increase this angular speed, now it is kept constant, like the linear speed is pretty much maintained around 0. But if I turn the linear speed controller off, then when I touch one of the wheels and it slows down, again the other one is sped up in order to compensate for this, so that the angular speed is controlled and kept approximately constant around the target. One final feature on this page is the command button at the top. This interface is basically exactly the same as the serial manager interface I demonstrated before. So you could type help, get exactly the same menu as before. You can also type any of the other commands in here, so whatever you want, and you will get all of the values in this text box. So it just allows you to get all of the debug information you got through serial, but over Wi-Fi. This is pretty much all of the features I wanted to demonstrate to you in this video. You can see that there is a very good base for the hardware, for debug, be it the serial monitor interface or the Wi-Fi interface. They both work, and it is a good base for development of more advanced software that would, for instance, allow to start navigating in a maze and maybe in the end solving the maze.